Here's another buckling problem. We have this particular configuration, which is we have a pin at the bottom. It's free to rotate at the top, so it's a pin-pin connection. The length is 240 inches, and we're applying 10 kips. The question is, does this buckle under this load? And we're given the Young's modulus, and this is the beam cross-section. It's called a W6x9 standard member. We haven't talked about these yet, but I'm just going to give you a little bit of background in that an I-beam, or what we sort of generically call an I-beam, in reality is not a perfect eye. It really looks, I've exaggerated a little bit, but it looks something more like that. And when you are in practice using standard beams, in other words, they're not custom made, you're using standard sections, then you can get the properties of that beam given to you. You don't have to calculate them out. In other words, you don't have to calculate out a moment of inertia for such a beam. And the meaning of the W6x9 is that the W stands for wide flange. In other words, the official name of an I-beam is not an I-beam. It's called a wide flange beam. W. And if you recall, this is the flange, and this is the web, and we call that the depth of the beam. And you can get the properties of these beams. They are either built into a computer program, or you can get them from tables. For instance, a typical table would describe the cross section. For instance, we can have a W8x12, W6x9, and the weight per length, in other words, pounds per foot, is given somewhat in the name. In other words, W6x9 has approximately 9 pounds per foot. Weighs approximately 9 pounds per foot. The depth of a W6x9 is approximately 6. Not exactly 6, but it's approximately 6. So when I give you W6x9, you know that the depth is approximately 6, the weight is approximately 9 pounds per foot. In tables like these, you're given moments of inertia, Ixx, Iyy. We've talked about the two different moments of inertia that you are interested in for such a thing, the moment of inertia about an XX axis. In other words, this is the moment of inertia about this axis, moment of inertia about that axis. The vertical one is the YY axis, the horizontal one is the XX axis. Okay, so given this situation, we can figure out what P critical is. We know that P critical is pi squared EI over KL quantity squared. So we have our pi squared, our E. Now, which I do we use? We have two I's here. What do we use? We've talked about it. We use the smallest one. So we use the smallest I. So K in this case, because it's pinned, is 1. And L is 240 inches. We get our P critical for that particular column is 12.26 kips. And what do we see? We only apply 10 kips, so it does not buckle. Now, what we are covering is what's called general buckling. Just to let you know, and as you go in further in classes, there could be local buckling. What do we mean by local buckling? Well, for instance, say there's our wide flange beam or I-beam. What can happen if we apply a load like that? Well, suddenly the web is a compression member in a sense, and we can get buckling of the web. The flange can also buckle. How can that happen? Well, when we bend our beam, we get our stresses looking like that, and in this situation we have compression at the top. And anytime, we'll put it this way, when you have compression, you have a situation where you have to, at least look at buckling, and possibility of it. And what can occur is if this compression is too high, then the flange will buckle. You'll see the flange going like that due to bending. So you can, in other words, there's local buckling. We're looking at general buckling, just to be aware that there is local buckling as well. Now, I want to look at the stress-strain curves. If you remember what stress-strain curves are, for instance, in tension. You've looked at these in previous classes, and what do you find? You find that it's linear initially, and then as the tension goes on, you can increase it beyond the linear range, and you get some more resistance, and then eventually you get fracture. Now, typically, the way that you see these curves drawn is you get an X there. And they draw them, and maybe they put an X or something like that at the end, meaning you have fracture. Well, if you take it a little bit and look at it in a slightly different way, you load, and you're getting resistance, more resistance, more resistance. Then what happens, you get fracture, and then it takes no more stress, but you get a lot more strain. So another way to draw the stress-strain curve would be something on that order. If we look at not tension, here's stress-strain curve for tension, but instead we look at our stress-strain curve for buckling, or for compression, which could lead to buckling, then what does that stress-strain curve look like? Well, we'll plot P versus delta. In other words, the load versus the deformation, and what we find is that looks something like this. We get a linear behavior, and then what happens? The buckling takes place. It can resist no more load, and we get a lot more deformation. So there is a much more dramatic loss of support or resistance when you have buckling. And so here's the thing. I want to illustrate this to a certain extent with something like this. Now, what happens, for instance, let's suppose that I have built this in a particular way. Here's my structure. I'm standing underneath this structure here. And what happens if one of these columns is undersized? What's going to happen? Let's suppose, for instance, that this column is undersized in this situation. If it's undersized, what happens? Well, it buckles. If that buckles, then what happens? that the load supporting, or this column takes no more load, because why? Because it's, we get total loss of support. That means that this weight must be supported by just the two remaining columns. Well, what occurs then? Well, then we find that that column likely is undersized. And what happens to that column? Then this column buckles as well. And then the next thing you know, that I know the geometry is a little bit weird, but let's just say then the entire load is then transferred to this column, which happens, and then this one buckles also. So that we get this progressive failure where this one buckles, then this one buckles, and then this one buckles. And in other words, when it comes to buckling, if you have a buckling failure in your structure, then you can get a complete catastrophic failure. And I put this person there because that person isn't going to be alive anymore. So in practice, buckling is critical. And you cannot have a buckling failure. If you have a buckling failure, you're going to have a catastrophic failure where people lose their lives. You don't want that to occur. So I tend to be very strict in grading buckling problems because I want to focus your attention on them. And when you're in practice and you're evaluating buckling, you better get it right. In contrast, let's look at this structure where everything is in tension, where these members are all in tension. What happens if this is undersized? Well, if that is undersized, what do we find? Well, that means we're getting yielding here, and I have all this remaining resistance in that member. So it ends up that, yes, okay, you may get extra deformation in this member, but there's still a lot of resistance remaining. So the tensile type failures tend not to be as progressive, in other words, because you have all this extra remaining. Okay, I'll skip that. All right, so I want to review trusses. I know you've all solved problems with trusses in the past, but what we are concerned about is the buckling of a truss. And why is this an issue? Because when we create a truss, what do we know? Well, truss members are long, skinny members. By definition, that's what they are. And as opposed to beams, beams are short, fat members. Trusses are long, skinny. So when you have a long, skinny member, you have to worry about, buckling is often critical. So when we are looking at our trusses, we're worried about the buckling of truss members. Now, which truss members are going to buckle? Well, the ones that are in compression. If a truss member is in tension, it's not going to buckle. So let's just review very quickly how you analyze this very simple truss. It's just a triangle. And because I'm going to give you a truss, and then I'm just going to tell you to evaluate buckling of the members in compression. So our goal is to determine whether member AC and member BC, whether they buckle. If we look at this problem is pretty straightforward in the sense that I can see clearly that AC and BC are in compression and AB is in tension. Why do we know that? Because, this, to exaggerate it, I'm pushing down here, this point is going in that direction. This point is going in that direction. So this member is in tension, and then these two are in compression. So, and we can verify that with the calculations. So how do we do this? The first thing we're going to do is we're going to create a free body diagram. We're going to look at that particular joint right there, joint C, and there's our free body diagram. Typical way we do it, we have our point, we draw the unknown forces away from the point, which of course it's away from the point, which means we're showing tension. It's a traditional way to do this. And then we're going to label this one FAC because it's from A to C, this one B to C. And then we have to get the angles correct. I always recommend that we always write our angles with respect to the x-axis. So don't draw your angles with respect to the y-axis, simply because you can simplify things if you draw them with respect to the x-axis. Why is it better to do with respect to the x-axis? Because that means our x component is going to use the cosine of the angle. The y component will use the sine of the angle, and that makes it very simple. So I convert this free body diagram to this free body diagram. They're identical, but I'm going to use the components. So I have for FAC, I have the vertical one is FAC sine 60. The horizontal one is FAC cosine 60. For the FBC, the vertical one is going to be FBC sine 60. The horizontal one is going to be FBC cosine 60. And then you get the directions right because notice I look at this force here, it's downward to the right. So I have a downward and to the right. This one here is downward to the left. So I have downward to the left. So if you get those correct, then you can look at this free body diagram. I'm now going to take the sum of the forces in the x direction. So in the x direction, I just have that and that. I have FAC cosine 60 minus, because this one's going to the left, so it's minus FAC cosine 60. This one's to the right, so it's plus FBC cosine 60. Those are equal to 0. And in this particular case, it's simple because the cosine 60s cancel out, and I get FAC equals FBC. Then I take the sum of the forces in the y direction equals 0, with upward being positive. So I have what? That's negative 10. Everything's going down, so everything's negative. Minus FAC sine 60, minus FBC sine 60. In this particular case, it's easy to solve these problems because I use that FAC equals FBC. I put in FAC for that one, and I get that FAC and FBC are the same, and they're both negative. What does that mean? If they're negative, then what? These directions reverse, and now they're pointing toward the body, toward the point, and that means that we have compression. And if I look at my member AC, I'm going to see that I have what? 5.77, 5.77. And then to determine whether or not we have buckling, we're going to compare that 5.77 to the P critical for that particular member. Okay, so let me do one slightly different. Okay, Well, this is the same problem, I guess. So now this is 12 degrees, this is 150 pounds. It's the same problem. I'm not going to go through it in detail. I create that free body diagram by looking at that point, and I then convert it to this free body diagram, and I get these equations, and I solve it in the same manner. So take a look at that. You know. Okay, we're going to make it a little bit more complicated by no longer having the force vertical and no longer having an equilateral triangle. How do we account for that? Well, and in this case, all we're going to do is find the forces. Like I say, this is a review for trusses. Find FAC and FBC. Well, the first thing we have to do is we have to break that into components, and as I said, you're best off using only an angle with respect to the x-axis. And if we do that, then like I said, we know that in the y direction we're going to use the sine of the angle, and in the x direction we're going to use the cosine of the angle. And so we look at this, we go, this is downward to the left. That's downward to the left, so I'm going to have downward to the left. And so this one's going to be 10 sine 30, that's the y. This is going to be 10 cosine 30. And here, this is given information. I'm giving you that that's 50 degrees, and I'm giving you that that is 20 degrees. So when we draw our free body diagram, here is our applied load, 10 sine 30 downward, 10 cosine 30 to the left. We've got our FAC at 50 degrees. We've got our FBC at 20 degrees. And what I'm saying is you need to be able to solve this problem. How do we do that? Again, there's our free body diagram. What do we see? This is downward to the left. So I have FAC sine 50 downward, FAC cosine 50 to the left. This is downward to the right. So I have FBC sine 20 downward, FBC cosine 20 to the right. So then we create this free body diagram, and we are now going to solve this. And the way we're going to do it is we take, of course, the sum of the forces in the x direction equals 0. Positive to the right, so I'm looking at my x direction minus FAC cosine 50 minus 10 cosine 30 plus FBC cosine 20. That's one of my equations. I do the y direction, so the force in the y direction, upward being positive. So I have minus 10 sine 30 minus FAC sine 50 minus FBC sine 20. All that's equal to 0. And notice when I look at, if we've done things like, say, if we put all of our angles with respect to the x-axis, then I look at my equations, and what do I see? I see in the x direction, all I see are cosines. It just makes your life a little bit simpler without thinking about them all. And in the y direction, all I see are sines. It's just an easy way to avoid mistakes. But now we have two equations, two unknowns, so it's a little more difficult. I'm not going to go through this. You should all be capable of doing it. or you should all be able to use your calculator to be able to solve this. So however you want to do it, you can set up basically these expressions. In other words, I simply put in the sines and cosines and moved the 10 cosine 30 and 10 sine 30 to the right hand side. Set up this set of equations so that you can put them into your calculator or solve it. So I'm not going to go through this. You can read this. I've done it longhand, but you are expected to be able to solve two equations, two unknowns. Okay, I'll stop there. Well, one second thought. Tell you what, I want you to do this problem. So pause the video and solve this problem yourself. So I've given all of the angles with respect to the x-axis here. I've given the load, and what you need to do is to first find the forces in member AC and member BC. Start there. So I want you to pause the video and use the method that we have just done and find the forces in those members. The next step will be to find P critical for AC and P critical for BC and determine whether or not they buckle. Okay, so I'm assuming you've solved that. I'm going to take you through the first part of it, and then we'll finish it in the next video. So, okay, so at this point you should be able to do this very quickly. I've got the 20 kilonewtons here at 80 degrees, FAC at 70 degrees, FBC at 40 degrees, and then I'm just going to convert that free body diagram into this free body diagram. And what do I know? This is downward to the left, so I have FAC cosine 70 to the left, FAC sine 70 downward. This is downward to the right, so I've got FBC sine 40 downward, FBC cosine 40 degrees to the right. This is downward to the right, so I have 20 sine 80 downward, 20 cosine 80 to the right. I now have this, and I create the sum of the forces in the x direction. You can all do this. By looking at these, I'm looking at the x direction. I've got those three. I take the sum of the forces in the y direction. I look at the y ones. I've got that. And so now I've got my two equations, two unknowns. You need to be able to solve this. You find that. I guess I'll finish this problem here with this video. So, okay, what else do we need to do to solve this problem? Well, I have, this is the cross-section for member AC. This is the cross-section for member BC. And I need to find the moment of inertia. Well, which moment of inertia am I going to use? Now remember, I want the smallest moment of inertia. Well, the smallest moment of inertia is about this axis, not the horizontal axis. So notice 112 BH cubed, well, the B is the 0.4. The H is the 0.1. I have to get that one to get the minimum moment of inertia. Same thing for this one. The B is 0.5. The H is the 0.05. So don't get fooled if I show you the cross-section like that. You have to know how to get the smallest moment of inertia there. So I get these moments of inertia, and then I have what I have. P critical for AC is going to be pi squared E I. Well, what's my K? My K, because it's a truss, everything is pin pin. I have pin 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 pin. So the K for truss members is 1. So this is simply L squared. And I'm not going to go through it. You can all use geometry and the Pythagorean theorem and geometry and figure out, this is the Pythagorean theorem. The square root of the sum of the squares of the legs gives me the length of that member, and I get 17.6 kilonewtons. And then for this P critical, so that's the property of that member. So how about the other one? Again, pi squared, E is given, I we just calculated, and there's the length of member BC you can get from that. Here I get 1.29 kilonewtons. So what do I compare those to? Well, we figured out that FAC is 13.68, but the P critical is 17.6. It doesn't buckle because our actual compressive force is less than P critical, does not buckle. But if we look at the other one, what do we see? We have FBC is negative 10.64. Well, our P critical is only 1.29, so it buckles. Okay, we'll stop there.